Let me say a couple of things before we get started. So next week, so Monday, no class. So this is due to Martin Luther King. And then on Wednesday, we're still trying to decide how to proceed. I'm going to be out of town on Wednesday, so we're seeing if Luis either can teach the class or we can post some material online. But please check the website of the course to get updated information as to what's going to happen. Okay, so check the website. Was that? Correct. Be careful with the camera. Yeah, if you move too violently, you may owe me a camera. Okay, so that's sort of the information to begin. What I wanna, let me perhaps, no, right? Okay. Okay, let's get started. So last time, we thought about a couple of things. The first one was this idea of nerve complexes. In particular, we saw the baby nerve lemma. And what the baby nerve lemma says is that if you compute the nerve of a collection of balls in this case, if you compute the nerve, or rather, maybe we can say it like this: if you compute the check complex of a collection of points in Euclidean space, then this has the same topology as that of the collection of as the region covered by the balls, right? So it's saying that the nerve is a reasonable construction to recover topology. So this is the nerve of these collections of balls. Okay. Yes. I do mean that. I mean that they're homotopy equivalent, actually. The second thing we saw about nerve complexes was a method to do learning with them, right? So this idea of learning with nerve complexes. The last thing we did was this idea of how to relate different simplicial complexes, and we covered the idea of a simplicial map. Okay, so what I want to do today is I want to connect particularly the simplicial map perspective that works at the level of abstract simplicial complexes. I want to connect it to the geometric picture of realizing geometrically realizing abstract complexes. That's what I want to do today. So let me start with a very simple comment. Yeah. So I'm going to let U0 through UK in Rn be affinely independent. And just to remind you what that means, that if you take u0 minus u1, u0 minus u2, dot, 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 u0 minus uk, then these guys are linearly independent vectors. In the linear algebra sense. You can replace u0 by any other vector. You can say, for example, uj minus u1, uj minus u2, and so on. So that's what affine independent means. Every time you have k plus 1 affinely independent vectors in Rn, then you can construct the geometric simplex. Right? Which is, which we've denoted as such, and is the set of all convex combinations of the form where the lambda j's are non-negative and they add up to 1. Okay, so the geometric simplex. Okay, so let me fix a point x in the geometric simplex. What I want to do now is I'm going to try to figure out how many different ways do I have of choosing the lambdas. Okay. Right, so for some choice of lambdas. Okay, let's see what other choice would do. So let's say that I could write it also as the sum of some betas, like so. Where again, so yeah, say that these are equal to the betas, where the betas again are non-negative and add up to 1. And what I claim is that the lambdas, in fact, have to be equal to the betas. Okay? So let's see why that is true. Yeah, so let's see why. So for example, so 0 is certainly equal to 1 minus 1, which is going to be the sum j0 from 0 to k of the betas minus the lambdas. Correct? So in particular, lambda 0 minus beta 0 is equal to the sum j equals 1 to k of lambda of beta j minus lambda j. Okay. Okay, cool. So I'm going to use this in a minute. But if these two things are equal, then their difference is, of course, 0. Right? So now 0, the vector, k of lambda j minus beta j of uj. And this is the same as writing, you know, lambda 0 minus beta 0, u0, plus the sum j equals 1 to k of lambda j minus beta j uj. And from here, this is the same as what is it? The sum j1 to k of beta j minus lambda j of u0. Which hopefully you can see is equal to the sum lambda 1, so lambda j minus beta j of, so how should I do it? Let me do it like this. Beta minus lambda of u0 minus uj. Right? So since the since u0 minus u1, u0 minus u2, all the way up to u0 minus uk are linearly independent, right? Then this can only happen if these scalars are 0, right? Because I found a linear combination of these vectors that give you the 0 vector. So that implies, in particular, that beta has to be equal to lambda. So beta 1 is equal to lambda 1, all the way up to beta k equal to lambda k, right? And if all the beta 1 through beta k are equal to the lambdas, then in particular the zeros also have to be equal because they add up to 1. Right? So we've shown that if I give you k plus 1 vectors in Rn that are affine independent, then when you form the geometric simplex that they span, then every point in here can be written uniquely in terms of some choice of lambdas. Okay. Omar, you have a question? Yep. Mm-hmm. Oh, yeah. So here's what I did. I took this expression for x, I took this expression for x, and I subtracted them. So I did this minus that, right? So that is 0, right? And we can certainly split this sum by taking just the first term in the sum, which is the 0th. That is this, and then the rest are these guys. Yep. That's exactly what it tells you, that every point has an associated specific collection of lambdas that describe it.
All right.
Yeah. So right, so the conclusion is, so it doesn't hurt to write it. So that is, for any x in this geometric simplex, there exists unique lambda 0. And I'm going to put an x in here just to make the point that it really depends on x. With such that x is that linear combination. Okay? The vector, or the collection of these lambdas, are called the barycentric coordinates of x. These guys over here. These are called barycentric. Coordinates. The geometric picture perhaps helps. So the picture is the following. If this is u0, this is u1, and this is u2, right? Then any x, and I'm thinking of this as the two simplex. You can write it as a combination of these three, okay? And then if, I guess I'm gonna write it, I'm gonna draw it like this. Boom, boom, boom. Like that, okay? This quantity over here it's supposed to be lambda 0. This quantity over here is lambda 1. And this quantity over here is lambda 2. Okay? The idea being that if this is 1, right, then the other ones have to be 0, and it just puts you on U0. So that's the geometric picture. Now, if you have not only a geometric simplex, right, which is just one of these guys, but let's say now that we have a geometric complex. All right, so let K, let me put it inside some Euclidean space, as we always do. Right, so a geometric complex. So, you know, perhaps it looks like this. And, you know, maybe it's got a 2 simplex in here. And this is, you know, U0, U1, U2, U3, U4, U5, and U6. And I'm thinking of it perhaps inside R2. Right, so say that you have a geometric complex like that. And let's fix a point in the geometric complex, a particular x. So I'm going to put it here. Okay, so given that x, we can find a unique maximal simplex that contains it in the interior. Does that make sense? So it is either here, or if it is an edge, then this is the, if it's here on the edge, then this would be the simplex that contains the point x. If it is a vertex, then it's a vertex. Okay? So for every point in my geometric complex, there is a unique simplex of maximal dimension that contains my point x in the interior. Once I've identified the simplex that contains my point, then I know that we have barycentric coordinates for this point associated to these vertices. Okay? So you can think of this point as described by lambda 1, let's say lambda 2, lambda 3, right? And all the other ones, we're just going to make them 0. Right? So lambda 3 doesn't participate because U3 doesn't participate in the combination, right? Similarly, lambda 5 is 0, lambda 4 is 0, and lambda 6 is 0. Okay? So every point in my geometric complex can be described, as we said before, uniquely with respect to its barycentric coordinates. And you just have to tell me what these values are, and I'll be able to tell you, you know, without any doubt where the point is. I'm going to use this idea to turn my simplicial maps into maps between geometric complexes. That's what I'm going to do now. Yep. Exactly. That's exactly what I mean. That's exactly what I mean. Yeah. So, for example, let's take a point in here. Okay. So this point is in this edge, and it's also in these 2 simplex. However, this point is not in the interior of the 2 simplex. It's in the boundary. So when we look at the edge, it is in fact in the interior of the edge, right? Because the boundaries are these 2 points, right? So what would be the simplex that contains this point? It would be this guy. It would be the simplex of maximal dimension that contains it in the interior. Okay. The one with the higher dimension, such that the point is in the interior. You need the 2. Okay.
Where you were able to find where exactly it is.
Mm-hmm.
Is that just within the simplex, like terms of simplex?
Correct.
You couldn't match the fact.
both. I could do both because I have coordinates for all these vectors. I can do both. Okay. Okay. So this idea of barycentric coordinates was the thing that powered the NERF learning methodology I explained on Monday. Right. Okay. Let me now go back to this idea of simplicial maps and how these barycentric coordinates help. So recall that if you have two simplicial complexes, and by this I mean abstract, then a function f from k to L is said to be simplicial if every time I evaluate f on a k simplex, it is essentially the same as taking the values on the vertices and taking the particular simplex I get. Okay. So let's say that we start with two abstract simplicial complexes. And for all intents and purposes, we only care about finite objects because, you know, data science. The idea is going to be the following. So say that I have two simplicial complexes. I have a simplicial map between them, and I also have a geometric realization for both of them. So say that we have inside Rn, and perhaps L inside Rm. Where, I'm thinking of the vertices of K. Say that the vertices, right? So this is say that these are vertices. This goes to, uj in Rn, and these yj goes to maybe vj in Rn. Yeah, what do I mean by this? So remember that, how do you realize an abstract simplicial complex? You have to tell me where the vertices will go, right? So I'm saying that the jth vertex is going to go to this vector, and you want the things to be finally independent so that you can fill in the appropriate geometric simplices. Then this simplicial map induces a continuous map. Say big F from the geometric realization of K to the geometric realization of L. And what does it do? So it takes, it takes a point in here, and we're going to send it to this is going to make sense in a second. And let me explain these notation. Oops. Yeah, there we go. Okay, so what is this notation implying? It's saying, take a point in the geometric realization of K. right? So any point in here can be written uniquely in terms of barycentric coordinates, in terms of the vertices of this guy, right? That's this picture. Those are the U's. And what I'm saying is that UXJ is, the U that corresponds to the vertex X. And similarly, V of this guy is the vertex that corresponds to the vertex Y in here. Okay? So the only thing I'm doing is look at the vertex X inside the abstract simplicial complex K. That corresponds to an actual vector inside the geometric realization. Now, any point in here can be written as a linear combination, as a convex combination of these vectors. Boom. Where am I going to send that guy? Okay, I'm going to look at what is the vertex in here. It's an xj. Where does that go through F? Oh, it goes to F of xj. What is now the vector in here? Oh, it's going to be a V. It's going to be V of that, and we just put the same lambdas in front. Okay, so that's the function. So any simplicial map is going to induce a continuous function at the level of simplicial complex, of geometric realizations of simplicial complexes. And here's where things get interesting, right? Because what we showed on Monday is that these types of constructions, these simplicial complex constructions, can be used to do learning on data that underlies the complex. Okay? What this suggests is the possibility of learning complicated functions between simplicial complex representations of data, right? So this can be, again, the space of dogs. This can be the space of cats. And you want to see what is the cat that looks most similar to the dog that you started with, right? So this opens the door to do learning between complex spaces using these locally linear representations. Okay? Did I say continuous? Yes, I did say continuous. Okay, I have a question for the class. I'm going to use the following notation. I'm going to say that F is going to be the geometric realization of little f. Okay. So this is the one that I started with at the level of simplicial complexes, and big F is the one I just defined in this fashion. Okay. So here's the question for the class. Does every continuous map say F from K to L arise as F of geometric realization for some simplicial map so what I've done here is I've shown you a way of turning a simplicial map between abstract simplicial complexes into a continuous map between their geometric realizations. Question, now say that you've been given just a generic continuous map from here to here. Can I write that down as the geometric realization of some simplicial map? Say yes. Okay, let's see a show of hands. So raise your hand if you think yes. Okay, we have a couple people. Raise your hand if you think no. Okay, split. In particular, it's not the complement. Let's see. Maybe an example would help, right? Let me do the following. let's say that that K is maybe x0, x1, x2, and then x0, x1, x1, x2, and x0, x2. And L is K union x0, x1, x2. So again, the picture is, this is K, and this is L. And I'm going to define the following simplicial map. I think it'll help. So let's say that F from K to L is going to send x0 to x0, x1 to x0, and x2 to x2. Okay. So what is the map doing? The map is sending these to that, and these to this. Okay. Therefore, where is it sending the edge? To this point, right? So it's collapsing the entire edge. So the entire circle is just being mapped to this edge right here. Okay. Let's see now what the map F looks like when I geometrically realize it. Right, so the geometric realization of F on something that is going to look like lambda 0, u0, plus lambda 1, u1, plus lambda 2, u2, right? So what did I say? I'm going to put the same lambdas here. Then I'm going to look at what F does to the corresponding vertex. So this is x0, x0, x2, right? So it would be, v0, v0, v2, which is okay. So that's how these maps look like. In particular, hopefully you can see that they are linear on each simplex. They're locally linear. So this is very unlikely to be true unless you only think about linear maps as the true maps. Okay? So let me give you an example as to why. Yeah, go ahead.
Like, couldn't you just send it to just the average of
I think that's right. Yeah, to the middle. Yeah, we can do that. Yeah, yeah. It doesn't. Yeah, that's exactly right. Yeah. But I want to choose another one. Okay, because of my next trick. So the other example I want to do is so maybe example 1 just to illustrate the construction. And then example 2, so let's let F, I'm going to choose particular geometric realizations for these two guys. Okay, so the geometric realizations I'm going to choose are as follows. So I'm going to put, so this is going to be 1, so I guess 1, 0, and this is going to be 0, 1. So this is how I'm going to realize K. And I'm going to realize L like so, 1, 0. Let me see how I noted that. Okay. So this is supposed to be U0. This is supposed to be U1. It's supposed to be U2. Yeah. is supposed to be V0. And V2, okay? So here are a couple of maps. I'm going to take G0 of xy to be just the identity. I'm going to take G1 of xy to be x comma y squared. And these are maps from K to L. Right, so one of them, so one of them is essentially just the inclusion of K onto L. And the other one is sort of bowing the, right? So in particular, this guy cannot be the result of a simplicial, of a geometric realization. This guy does not come from a simplicial map. And again, the reason is because it is not locally linear, right? So if it is not locally linear, in particular, this is not linear, then it cannot come from something simplicial. Okay, but I do want to use this example for something else, for my second question. Okay, again, if this is not clear, the answer is no. I'm going to give you a definition, and then I'm going to give you the next question. And hopefully this example will help you. So here's the definition. Two continuous maps G0 and G1 from K to L are said to be homotopic. And you're gonna hear that word a bunch of times, homotopic. If there exists a function, a continuous function, G from K cross 0, 1 to L, so that G of x comma 0 is G0 of x, and G of x comma 1 is G1 of x. Okay. Homotopic. Yes?
Exactly the same homotopic as the top one.
Yep. I'm just doing it for a very particular type of spaces. Okay, so what does it mean to be homotopic? It means that you can deform continuously one map onto the other. In particular, if you think of this second coordinate, you can think of this as perhaps time, right? So it's saying that at time 0, you are at the initial map G0, and at time 1, you are at the second map G1, and the transition from one to the other is all a continuous process, right? So on day 1, we talked about this idea of deforming shapes into other shapes. The idea underlying it is something similar to homotopy. Okay, okay, great. So here's the question. Yes. Let me introduce the following notation. If G0 and G1 are homotopic, I'm gonna denote that as saying G0 squiggle G1. This is the notation. So this means G0 homotopic to G1. Okay, now we're ready for the question. The question is, does every continuous map arise as being homotopic to the geometric realization of some simplicial map? Does that make sense? So maybe your map F, big F, itself is not, it doesn't come from a geometric realization, but perhaps you can deform it a little bit and turn it into something that does come from a geometric realization. And the deformation that we are allowing are of this type. Okay? So that's it. That's the second question. Let me use this example to sort of drive my point home. So let's take these two functions. Okay, so this is example 3. Okay, so we've already established that this guy, the map G0, given there, it does come from a simplicial map because it's just the inclusion. There's nothing fancy there. The second map, G1, does not because it's not locally linear. But notice the following. So we're going to send the point x comma y and say the time variable t to the point x comma t, I don't know, y times 1 minus ty squared. Okay. So, so what is this map G doing? It is essentially, so if you think of what's going on in L, right? Right, so this is G0, say this is G1, okay? And what it's doing is essentially connecting these with like just straight lines. Right, that's what G is doing. And it's all happening, everything is happening inside of L. So it's good, okay? So this map, G1, does not come from a simplicial map, but it is certainly homotopic to one that comes from a simplicial map, okay? Okay, so now raise your hand. Again, we're gonna do a show of hands, see if democracy is aligned with math. So raise your hand if you think this is true. That every time I give you a continuous map, you can find a simplicial one that you can deform it onto. Okay, a few people. Raise your hand if no. Whoa, even worse now. Okay. This requires some work, but the answer is no. So there are maps, there are continuous maps that even with this sort of looser notion of deformation cannot be derived from simplicial maps. Okay, so simplicial maps give you, a lot, but not too much. I guess that's one way to think about it. Yeah, I don't know of an easy way to say why this is the case. So, but hopefully you can trust that I'm telling the truth. Let me say what is the case. What does simplicial maps give you? Okay. So there is this notion that, again, people that work in electromagnetics and sort of finite elements perhaps know about. And it's the idea of subdivisions of complexes, right? So barycentric subdivision. And I think the easiest way to describe it is with a picture. So what is the barycentric subdivision of a complex? So say that you start in the geometric setting. And I'm going to do, so here I'm going to put a complex, and here I'm going to put this barycentric subdivision. Okay. So if you take a vertex, and if you subdivide it, then you get the same vertex. We're thinking of it as the elementary block, right? So this is the complex. Bless you. And this is the subdivision. If you take an edge, then barycentric subdivision means look at the barycenter, that's this, and then put a vertex there. So this is the subdivision. So now I have 3 vertices. If you now look at a 2-dimensional face, the way you subdivide it is an iterative process. You start by subdividing the vertices, which doesn't give you anything. Then you subdivide the edges. Then you connect the barycenter of the face to all the edges. And that is the barycentric subdivision of the face. And you can keep going in higher and higher dimensions. So it just gives you a bunch of smaller simplices and a lot more vertices. You can also do it in the abstract setting, right? And I think it's actually easier. So here the complex is x0. And then its subdivision is just, is that. Still just one vertex. The vertex here is x0. The vertex here is the set containing x0. Just one thing. Here the complex is x0, x1. And then, let me do it right. So x0, x1, and x0, x1. Right? The subdivision then is, I'm going to have 3 vertices now. I'm going to have this vertex, which is x0. I'm going to have this vertex, which is the vertex corresponding to x0, x1. And I'm going to have the vertex corresponding to x1. And I'm going to have the edges between this vertex, and this vertex, and that vertex. So x0, x0, 1. And x1, x0, x1. So you can see how this can get cumbersome pretty quickly. But the idea, at least geometrically, hopefully makes sense. That you just put barycenters and then connect to everything you can. Okay, cool. So I'm going to use the following notation. If I have a complex K, either geometric or abstract, its barycentric subdivision is going to be denoted as SDK. Okay. Now, so here's a remark. One can choose geometric subdivisions. Sorry, one can choose geometric realizations such that if you realize the subdivision, right, you get exactly the same set as just realizing the complex. See what I mean? Sort of the points that are in here are essentially the same points that are in here, even if you now declare this vertex to be a vertex. Does that make sense? The second remark is that if you have a function g, maybe say f, from the realization of k to the realization of L, right? Then f extends, and I'm going to put this in quotation marks. Subdivision k to L. I'm putting the word extending in quotation marks because we just said that if you subdivide it and then realize it, you get essentially the same set as without doing anything. So this perhaps sounds vacuous in that I already had it on K. All I'm trying to say is that here you have more vertices. So this is a finer complex than this guy. And the third remark that shouldn't perhaps come as a surprise is that if you can take a complex and you can subdivide it, you can keep going. You can subdivide again and again and again. So one can iterate. SDN this is n times. Okay, now we're ready. So here's a theorem, super cool theorem. It says the following. For any continuous function f from K to L, big F, there exists some natural number and a simplicial map F such that how did I write it here? Oops, that's why it's false. From the subdivision of K into L, such that F is homotopic to the realization of F from big N. Natural numbers, yes. N, just a natural number, N, like 42. Just a natural number. So that if you subdivide sort of enough, then you can homotope your original map F into something simplicial from here. Mm-hmm. The new edge Correct. Yeah, so that's why I put the, you're right. How do I put that? What's her name again? Khalid. Khalid's comment, a very good one, is that when you subdivide, you're adding vertices, and if you're not careful, the vertices you get might not be affinely independent. Okay, may not be affinely independent. In particular, these three vertices are all on the same line, therefore not affinely independent. However, I'm only considering the edges between these two guys and these two guys. These two are affinely independent themselves. These are two affinely independent. I'm not considering the three simplex. That's a very good point.
So when you wrote the abstract or
Why are three edges here? It's confusing. I give you that. I'm thinking of this guy not as an edge, but as a vertex. It's a set, right? It's a set. Right? So is the vertex corresponding to the barycenter of this simplex? Yeah, I mean, maybe the notation is confusing, but yeah, that's a good point. Okay. So,
so yeah, so that would be the point of
correct. That's exactly right. Okay, so I mean, if you're used to thinking in terms of approximations like like Taylor series or Riemann integrals or whatever that requires subdividing your domain to get better answers, this is the content of this theorem. This is called the simplicial approximation theorem. And it says that, perhaps you can start with a very wild function, big F, from this realized object to this realized object. And as we've seen with the previous examples, maybe F doesn't come directly from a simplicial map, and it may even not be homotopic to a simplicial map. But what you can do is you can just subdivide your domain enough, and then you can find something to homotop it to that is simplicial. Okay, so that's the intuition. Okay. I'm gonna skip the proof. We don't need it. But I wanted you to know that these types of constructions, sort of simplicial complexes, geometric complexes, and subdivisions thereof, in particular simplicial maps, even though they seem very constrained because they have to be locally linear, they have a lot of meat to it. There is a lot that one can approximate with simplicial maps and their realizations, if you're willing to subdivide, which doesn't sound as crazy as. Okay, any questions before we continue? Okay, yeah. Mm-hmm. Yep. Correct. But that's too much topology. I mean, you said dense. Didn't you say dense? You said dense. No, but maybe it is not as hard to believe, right? That a continuous function can perhaps be approximated locally by linear things, if you're willing to subdivide enough. Maybe. Okay. Yeah, no. Yeah. Okay. So what I want to move on to now, that we have a way of comparing simplicial complexes, particularly with simplicial maps and geometric realizations and subdivisions and so on, I want to move on to homology. And we're gonna do it very, very slowly, right? The first thing I'm gonna define that we're gonna need is the idea of an orientation. Okay. Okay, so an orientation for an abstract simplicial complex of a complex K is a partial order on its vertices such that the simplices are totally ordered. And I'll say what that means in a moment. Are all totally ordered. Okay, so what do I mean here? So here's an example. So let's say that my complex is something like this. It has 4 vertices that we're going to call as always x0, x1, x2, and x3. And it's got the appropriate edges and faces. So we're going to define the following partial order. Okay, we're going to say that x0 is less than x1, and perhaps I should use a different notation for the order. Okay, so x0 is smaller than x1. We're going to say that x1 is smaller than x2. We're going to say that x0 is smaller than x3. And we only need one more, if that x2 is less than x3. Did I miss x2? Yes, I missed one. So x0 less than x2. There we go. Yeah. Okay, so what is a partial order? A partial order is a choice of saying what is smaller than what else. Right? So I'm saying that x0 comes before x1, x1 comes before x2. The one thing that the order has to satisfy is what is called the transitive property. That if x0 is less than x1 and x1 is less than x2, then x0 has to be less than x2. Okay? That's it. Now, what you would notice is, for example, I didn't say anything about x1 and x3. Right? I didn't say whether x1 was smaller than x3 or whether x3 was smaller than x1. You don't need to specify that. There may be pairs of elements that you could just not compare, right? You don't need to you don't need to establish an order where every single pair can be compared. Yeah?
But are they transitive or no sort of not?
How would this violate transitivity though?
I don't violate it.
Yeah. It wouldn't. It wouldn't.
But,
Yeah,
okay.
yeah. There are orders which do not. Here's an order. Say in the natural numbers. Here's a math. This is a math example. Right. So in the natural numbers, I'm gonna say that A is less than B, if and only if A divides B. Okay. So that's how I'm defining the order. Right. So for example, 1 would be less than 2. 2 would be less than 4. But how are 3 and 5 compared? They don't, right? So an order is just, again, very carefully saying what is less than what, but not all pairs have to be comparable.
Okay, I was just wondering because it looked like you could transit say x1 is less than.
Exactly. No, but that's not happening here. We're good. We're good. Okay? So this is the order. And now the thing that I want you to notice is that if you look at each simplex, so for example, let's look at x1 and x0. In the order, I know how to compare those two. if you look at 0, 1, and 0, 2, and 3, all these pairs are comparable. That's what I meant by the simplices being totally ordered. Means that when you look at each simplex, all the elements are comparable. Okay, you can check all the pairs in any given simplex. Why is this called an orientation, though? So it is an orientation because it suggests the idea that if x0 is, for example, less than x1, then perhaps there should be an arrow from x0 to x1. And that if x1 is less than x2, then perhaps there is an arrow from x1 to x2, and so on. Okay, so that gives you an orientation on all the simplices in particular. And here we think that 0, 2, and 3 go like that. That is this is the orientation induced by this total order. Okay, so an orientation is just a way of designing or sort of getting an order to tell you what the arrows look like. Matthew, was it? So Matthew asked a while ago, do I care about the order of the vertices in the geometric complex? This is the reason why I do. Because once you choose orders, they give you orientations. Okay? Yep. Uh-huh. That doesn't matter because there is no edge between x1 and x3. It's just superfluous. But if you did change one of these inequalities, I mean, it would have to be consistent, but it would change the orientation of the complex. Okay? Yep.
Should the arrow for
It should. Thank you. Because x2 is less than x3. Yeah. Yeah, but then when you go to 4 dimensions, then you forget about arrows and just keep the order. Okay, we won't need the arrows. I mean, the arrows are good for the geometric intuition, but what we need is the order for the formulas. Okay. Okay, cool. Okay, now we have orientations. Okay, so I'm gonna draw. Should I draw it? No, let's not draw it. Here's a remark. And it's gonna be sort of hand wavy, but hopefully it'll make sense. So if K is oriented, right? So if I found an orientation for the complex, and sigma is a simplex of K, then minus sigma, what do you guys think it'll mean? Flip all the arrows. Okay, cool. So now we can actually begin. How many of you know what a group is? Group, like algebraic thing. Okay, not many of you. So let me give you a definition. I'm not gonna define what a group is though. So given a simplicial complex, we define the K chains as the set CK. The notation is going to look weird. Ooh. Let's use N. K is a bad letter. N chains. Okay, so the N chains of K. And I'm gonna put a Z here, like for integers, for good measure. Of all functions so this is going to be all functions from phi, so all the functions phi from the set of n simplices of K to Z. So that's what this set is. That's what the chains do. The chains are just all the functions from the n simplices of K to Z. Z is the integers, yes. Right, so now let me give you the example. Now we can draw it. Okay, so let's say that K looks like this. So let's say that K is that. Boom, boom. And let me add one thing. Let me say that K not only is a simplicial complex, but I'm going to require it to be oriented. Okay, so you've chosen an orientation, meaning that you chose an order on the simplices so that everything looks good. Okay, so let's say that the order is given by the indices. Yeah, I'll often do that. I'll often say that this is less than this if the indices respect that law. So 0 is less than 2. So this goes like that. This goes like that. And 3, 5, and like that. Okay, so I've given you an oriented simplex. Okay. Now I'm going to give you an element of the one chains. So I'm going to give you, so I'm going to take an element in here. These are the one chains. Okay? And what do I have to do? I have to tell you what to do with every one simplex of K. Okay? So the way I'm going to do it is I'm going to say, there's a ton of them. Let me tell you the ones that are non-zero. I'm just going to write it, and you'll see what I mean. Okay? Yeah. So I'm going to let phi of x0, x1 be equal to phi of x1, x4. And I'm going to let that be equal to minus phi of x4, x5. And then I'm going to let phi of xij be equal to 0 for all others. Does that make sense? And equal to what? Yeah, that doesn't make sense. Equal to 1. Okay. So here is another way to write the same information. I'm saying sigma, the vector, not the vector, but the edge, 0, 1, is going to have a value of 1. Okay? So I'm just going to put the value in front as if it were multiplying. Okay? X1 and X4 also has value equal to 1. So I'm going to put that value in front as if it were multiplied. And it's actually plus 1, right? And then 1, 4, 5 has value minus 1. So this is another way to write phi. Yep.
I'm sorry, is your definition of there, is that the definition of phi right there?
It is the definition of phi right here.
So you're defining
I'm saying phi is a function and its values on the edges are the following. Yep. Cool. Cool. Okay, but what I want to stress is the geometry of this algebra. So what I'm saying is you're doing 0, 1, and you are doing it in this direction, right? Because it's positive. Then you are doing 1, 4, because it's positive. And then you are doing minus 4, 5, which is, I apologize. Now I will. I thought I was too. But yeah, but I messed up. Okay. No harm, no foul. We're good. We're back in business. The algebra is representing a path from 0 through 1 through 4 all the way up to 5, following the appropriate orientations of the edges, right? So that's what these coefficients are telling you. That's why these are called chains, right? You're connecting edges, right? Or you can also connect faces, triangular faces, and those would be 2 chains, or 3 chains, or 4 chains. Okay. Next time, when we come back, we're gonna define homology using these chains, because they're gonna be the way, or one way, in which we're gonna be able to measure with algebra things like holes in the space. Okay, so that's where we're going with this. Okay, have a good rest of the week, and I'll see you at some point. I'll make sure to announce on the website what the class on Wednesday is gonna be.